Today we will discuss weighted graph, shortest path and Dijkstra algorithm. Dijkstra algorithm is the one very important application of graph theory which is used to find out the shortest path between two vertices from starting vertex to ending vertex. So first we discuss what is the weighted graph. A weighted graph in which a non-negative real number w of e is assigned to its edges e. The number w of e is called the weight or length of the edge e. So now what? For example, we consider a graph this is your A, B, C, D, and suppose this is the E. If we assign a non-negative real number to each edge, which is called the weight of the edge. Suppose this is 3, this is 4, this is 5, this is 9, this is 2, this is 4, this is the 1. So such type of graph is known as the weighted graph. From weighted graph. Now today's our task is to find the shortest path between initial vertex to ending vertex. So in finding the shortest path, the initial vertex is always denoted by A and final vertex is denoted by Z. Now our aim is to find the shortest path between A to Z. There are so many paths exist in this graph here because this is the undirected graph, simple graph. So what are the paths between A to Z? First is A to B, B to Z. The length of this path is 2 plus 2 equals to 4. Another path is A to, suppose this is the E. So A to E to Z equals to 3 plus 4 equals to 7. Another path is A to E to C to D to Z equals to, this will be 3 plus 9 plus 4. A to E is 3 and E to D, sorry, this is the C point here. Okay, so here A to C to Z equals to 3 plus 7. So A to C, C to D and D to Z equals to 3 plus 9 plus 4 equals to, it is 16. And lastly A to D to Z equals to 1 plus 4 equals to 5. So these are the various paths between A to Z. Now our task is to find the shortest path among these paths. So we see the shortest path is here 4. The shortest distance is 4 and the shortest path is A to B to Z with shortest distance 4. Here the vertex set is very small, A set is very small, but we have large number of vertex and large number of edges. Then in this case it is very difficult to find out by this method. This is known as the observation method for finding the shortest path. So when the graph is very large, then how we find the shortest path between two vertices? Then we use Dijkstra algorithm. And this is the very most important application of graph theory, to find the Dijkstra algorithm, to find the shortest path using Dijkstra algorithm. Now we discuss this is the weighted graph. Okay. Now what is the weight of a path? Let G equals to V comma E be a graph. The weight or length of a path in the weighted graph G is equal to the sum of weighted of the edge in the path. What is the weight? Now the weight of this path is 4. The sum of weight of all edges. So how many edges here? A to B and B to Z are edges, and their sum is gives the length, gives the weight of the path. Okay. Similarly, we have this is the weight of path for this is 7, this is for 16, this is for 5. Now what is the shortest path? Shortest path between shortest path between any two given vertices of a weighted graph is defined as the path of minimum weight or path of minimum length. Now, just we see here ki which one is minimum among this path. The 4 is the minimum among them, so that the shortest path of this graph will be A to B to Z. Now we discuss the Dijkstra algorithm. This is the one very important application of graph theory, is to find the shortest path of minimum weight or length. That means to find the shortest path between any two given vertices of a simple weighted graph. For this we use Dijkstra algorithm. For this we use Dijkstra algorithm. In shortest path, we always call the starting vertex as A and the final vertex as Z. That means we have to start the path from A and we have to end at Z. The sum of weighted on its edges gives the total sum of path P, and we have to find the shortest path. That means the path, so here what is the P? Here is the P equals to, we denote this path as a P. This is the P. We have to sum of the weight of its edges is minimum from A to vertex A to vertex Z. That means we have to path which has the minimum distance from A to from Z. So there are two situations, different types of shortest path problem. First is shortest path between two specified vertices, and shortest path between all pair of vertices. So for first shortest path between two specified vertices, we will use Dijkstra algorithm. Now, what are the Dijkstra algorithm? This is a very important question. In examination mainly ask explain the Dijkstra algorithm to find the shortest path, or example based on shortest path using Dijkstra algorithm. Now, what are the steps involved in Dijkstra algorithm? The shortest path between two specified vertices. So here we are taking vertex A, and here we are taking the vertex Z, and we have to find the shortest path between A to Z. The following are the steps in a graph in Dijkstra algorithm. Step 1. Consider the starting vertex as A and denote it, we denote this is the point as a starting vertex A. Let P equals to A, yani ki we are generating a path P equals to A, because we are starting how many vertex, what vertex will be in the path. First we have to find. So we are starting vertex is A, so we generate a path P equals to curly braces A, and we create a subgraph for this one, T equals to V minus A. V is the vertex set, okay, and for the subgraph T is generated by eliminating the vertex A from vertex set A, from the vertex set. So let P equals to A and T equals to V minus curly braces A. Then for every vertex T in T. Now this is T into T. For the remaining vertices, we calculate L of T equals to W of AT, and this is the known as W of A of T is known as the weight of edge from A to T. Where W of A comma T is the weight of the edge joining A to T. That is, if we define W A comma T equals to N. N is the number which is the weight given on given edge. If it will be N, if A and T are adjacent to each other, then we put a number, the N, capital N, and capital N is the number which is given on given edge. Okay, if they are directly connected, then we put N. Otherwise, if they are not adjacent to each other, then we put infinity. If E edge is between them, then we put, if E is not as between them, then we put infinity. Otherwise, we put capital N here. If no edge is incidence on A and T, that is A and T not directly connected or not adjacent to each other, then we put infinity. The simple example is, suppose this is the any graph. Okay, A to B, C, D, and this is the Z. Okay, here A and C are not adjacent to each other. So what is the length of A comma Z equal to infinity? Suppose this is 2, 3, 4, 3, 9, 2, 1. Here A and Z are not directly connected. That means they are not adjacent to each other. So we put A comma Z equals to infinity. But what will the value of A comma B? The A comma B will be 2 because they are adjacent to each other. So we put W of A comma B equals to 2. Okay. So similarly we can find the W of A comma T for all other vertices, and where T belongs to capital T, and capital T is the subgraph of G, or which is obtained by removing one vertex A from V. Step 2. From the above obtained weight, L of T equals to W of A comma T. Select the vertex in T that has the smallest index with respect to T. Now we have to find the value which is having the minimum value among various W of A comma T, where T belongs to T, and denote this smallest or minimum weight, and we denote this smallest weight as a X. Step 3. If the index or label of vertex Z, then stop the algorithm, and the path P union of Z will be shortest path. Otherwise, P dash equals to P union of X, and T dash equals to T minus X for every T belongs T in T. We compute its smallest index with respect to P dash using the relation. Now we use the relation. After finding the weight of index of initial vertex, then we use for the remaining vertices from A to remaining vertices. How we find? The formula is L dash T equals to, this is the formula, L dash T equals to minimum of curly brackets L of T comma minimum of L of T comma L of X plus W X comma T. This is the formula for finding the index of various vertices from A to other vertices. Now we use this relation. So we have two main formula here. First is L of T equals to W of A comma T. This is for initial vertex, and for the remaining vertex other than A, we use this relation L dash T equals to minimum of L of T comma L of X plus W of X comma T. Now repeat the step 2 and 3, and repeat until we have reached to the vertex Z. Until we have to reach to the final vertex Z, and stop the algorithm. This is the end of algorithm. So we have total 4 steps in Dijkstra algorithm. We already discussed here. Now we take an example ki how we find the shortest path of the given graph, and this is the very important part ki how we find the shortest path using Dijkstra algorithm. We have to remember two formula here. First is L of T equals to W of A comma T, and another is L dash T equals to minimum of L of T comma L of X plus W of X comma T. Now we consider an example here. Now we write this example here. Now this is A to B, vertex A, this is B, this is C, and one vertex is directly to Z. Okay, and we have to find B. Here is C. Okay, directly. Okay, so this is okay. Sorry. A to B, this is your C, and this is your D, this is E, and this is F and Z. The length, the weight on A to B is given 22. This is 10 and this is 8. So A to B, the weight is given 22. Then B to C is 20 and C to D is 10. And from B to E is 2. This is 4. From C to Z, 10. From B to F is 7. And from C to E is 4. And from C to F is 3. And another edge from B to Z, and this is 2. This is the length of this edge is 2. So this is the graph, and we have to find the shortest path from A to Z. Okay, now we start Dijkstra algorithm. First we consider the vertex set. Here vertex set is V equals to A comma B comma C D and E F and Z. This is your vertex set. Vertex set is A comma B comma C comma D comma E comma F and Z. Okay, now we start with step 1. Step 1 is, let's consider starting vertex as A, and so we create a path by taking this P equals to A. This is the path, starting vertex, and the remaining vertices in TR. The remaining vertices are TR. T equals to V minus S. You have to remove A here. So we get T equals to, the other vertices are B, C, D, E, F and Z. These are the other vertices. So our path is P, starting vertex we are taking, and the remaining vertices are B, comma C, comma D, E, comma F and Z. The next step is, now for every T in T, very T is a small t to capital T, we compute smallest index from A to all other vertices in T. So now we have to find the weight of the edges from A to all other vertices, or it is given by, the relation is L of T equals to W A comma B. We are using this formula here. Okay, so what will be the weight, smallest index? What is the index of the vertex A to B? Here we check here. Here T belongs to T, so we are taking here T equals to A. So W A comma B, the formula is, we have already written here, L of T equals to W A comma T here. So here we are taking the first element of capital T, which is B. So what is the index of W A comma B? So here the distance is given 22. So W A comma B equals to 22. They are directly connected. They are adjacent to each other. So we put the number 22 here. Now for T equals to, the another element is T equals to C. So this will be W A comma C, and this is A comma C. They are adjacent to each other. So we put 10 here. Then T equals to D. So W A comma D equals to, this is the 8. They are directly connected to each other. Now W A comma E, we have to find the index from A to all other vertices here. So W A comma E, they are not adjacent to each other here because B is there. So we put infinity. W A comma F, they are not adjacent to each other. So we put infinity, and W A comma Z, they are not adjacent to each other, so we put infinity. Hence, the finite indexes are, that is 22, 10 and 8. So, and the remaining index for A to E, A to F and A to Z is infinity. So these are the smallest index. Now, sorry, these are the index. Now we have to find the smallest index among these index. Now select the smallest index from the above. In our case, the smallest index vertex is D equals to 8 here. Here we get this is the minimum value, smallest among all index. So we take, this is the for the vertex D. So the smallest index is for D, which is 8. So we select vertex D for the labeling and we put x equals to A. Yeah, we take x equals to D here. X equals to D. Now next. Now after selecting the D, our path will be increased here. Our path, what will be our path? We denote this path as, P dash equals to P union of the vertex which is we chosen here, D equals to, the now path will be A to Z. A to Z, and T dash, that means T minus vertex D. The remaining vertex set is, which will be B, C, E, F and Z. B, C, E, F and Z is the remaining vertex. And now again we have to compute the smallest index among B, comma C, comma E, comma F and Z. And what will be? It will be, we see here. Okay. Now you have to find the, first you have to find the index for T belongs to T dash, and the T dash having P, comma C, comma E, comma F and Z. Then what will the formula? Then for T equals to, we using the formula L dash T equals to minimum of L of T, comma L of X plus W of X, comma T. Okay. So using this relation, now we compute the smallest index from A to all other vertices in T dash using the relation L dash T equals to minimum of L of T, comma L of X plus W of X, comma T. So here we have take X equals to D. Here X equals to D, just we chosen in previous step. So X equal to D. Then what will the formula? The formula will be for X equal to D. The formula will be L dash T equals to minimum of L of T, comma L of D plus W of D, comma T. Now in this case, what is the T? T are the elements of T dash. So what are the elements in T dash? B, comma C, comma E, comma F and Z. Now you have to find the index of this one. So here, if we are taking T equals to here B, the elements will be, then the what will be the formula? This will be L dash B equals to minimum of L of T. T is here B, comma L of D plus W D, comma B. Because another pair here D, comma B is similar to B, comma D here. Okay. Then what will the value here? The minimum of, what is L of B? Just we find in the previous slide here. So L of B is, just we see here L of B equals to 22. So we put L of B equals to 22, comma L of D. Just we find this is the 8 plus, and distance between, yeah, weight of D, comma B. Distance between D and B is D and B. Just to see here, D and B, they are not adjacent to each other. They are not directly connected. So we put here infinity. So minimum of this is minimum of 22, comma infinity, because if you are adding any number infinity, we get always infinity. So 22, comma infinity, and the minimum is 22. So this is the index of L dash B. Similarly, we have to find the index of all other vertices of T dash. That means we have to find for C, we have to find for E, we have to find for F, and we have to find for Z. So directly we can find in this C. So T equals to C here. L dash T equals to minimum of L of C comma L of D plus W of D comma C, and the index of L of C is 10 in the previous slide. Just to see, this is the 10, and L of D is 10, and W D comma C, W D comma C, D comma C, they are directly connected. So we put 10. The weight of this edge is 10. So we put here 10. Then we get L dash C equals to 10. Similarly, we get L dash E equals to, and L dash F equals to, and L dash Z equals to. So L dash E is L dash E here is infinity. Why here infinity? Just we check out here. Now we're taking T equals to E here. So L dash T equals to E. So here L dash E equals to minimum of LB. So this is LE comma L comma D. This is fixed, and W D comma E. So what is the value here? So minimum of L of E. Just the previous slide, the L of E is just to see. L of E is infinity, and L of D, just we find the previous slide here. L of D is also 8 plus. Now W of D comma E, then weight of D comma E, they are not directly connected, they are not adjacent to each other, so we put infinity here. So the minimum of infinity comma infinity, we get infinity. So L dash T is also here infinity. Similarly, we find L dash F here. L dash F is 14. Similar way, so L dash, now here T equals to F here. So L dash F equals to L dash F, L of F plus L of T is fixed, and W D comma F here. So your L of A from the previous slide, what is your L of F? L of F is infinity here. L of F is infinity, and L of D is previous slide. This is L of D is 8 plus D comma F, यानी कि weight of index of D comma F. So DF directly connected here, and the length of D comma F is given here. So what is the length of D comma F? We have to find. This is 8. This is 6. This is 6, and this is 3. So the weight of D and F is 6. So we put 6 here. So this is infinity comma 14. The minimum of infinity and 14 is 14. So index of L of F is 14. We have already found out. Now index of Z. So now put T equals to Z. We have taken here B is completed, C is completed, E is completed, F is completed. Now Z. So T equals to Z. So L dash Z equals to minimum of L of Z, or LD plus D comma Z. Okay. So this is, now what is your L of Z? In the previous slide, L of Z is infinity, and L of T is 8, and plus W D comma J, they are not directly connected. D comma Z, they are not directly connected, so we put infinity, and this will be minimum of infinity comma infinity, and always infinity. So this is always infinity. So these are the index of remaining vertices of T dash, B comma C comma E comma F comma Z. Now we have to find the smallest index. So which one is the smallest here? Just to see, I think smallest is C. Now we take C. Now we add the vertex C in our path and remove from the T dash. So we create another path, P double dash equals to P dash union of, here we are adding the vertex C, we are adding the vertex C here. So this will be, our path is A comma D comma C, we are increasing our path, and here, and we remove D C from T dash, we get T double dash, and it will be, the elements of T double dash will be B comma E comma F comma Z. Okay. So what is the smallest index? Now smallest index for C, so we take x equal to C here in the algorithm. Now select the smallest index in above. We, our case, C is the smallest index, so let take x equal to C. Now C is not equal to Z. Now C is not our final vertex, so we continue the algorithm here. So we create the new path, just we discuss here, and T dash, our new T dash is B E F Z, and new path is P double dash is A D C, and we continue in the similar manner here. So P dash we already discussed, T dash we already discussed here. Now for every vertex T in T dash, T double dash, we compute the smallest index using the relation. This is the same relation here. We have to find the smallest index for remaining vertices B comma E comma F and Z. What happened here? See. Now we are taking the first element T equals to B here. Here the elements of T dash is, first element is B. Then what will the value here? So we put T equals to B. Here will be L double dash B equals to, the formula will be changed here, only change in notation here. In place of L dash T, we take L double dash of T equals to minimum of L dash T plus L dash D plus W D comma T, there is no change. Now L double dash B equals to minimum of L dash B and L dash D, here D will be replaced by C, sorry, here we are taking the C, x equal to C plus W D comma Z, so here will be C comma B, C comma B. Okay, so here L dash B, just we see, we are taking the elements B, L dash B comma L dash C plus W C comma B here. So put the values L dash B, minimum of L dash B, just to see what is the value of L dash B, just we find. So in previous slide, L dash B is 22. So 22 comma L dash C, L dash T is 10 plus WC comma B, WC comma B, C comma B, they are directly connected, they are adjacent to each other. So this is 20. So minimum of this 22 comma 30, that is 22. That is 22. So index of L double dash B, this is vertex B in the second iteration, that is 22. Okay. Similarly, find the index for E, index for F, index for Z using the same relation here. So what will the value here? Here will be L double dash E, L double dash F and L double dash Z. So using the same concept, same relation, we have L double dash E equals to 14 and L double dash F equals to 13 and L double dash Z equals to 20. So now we have to choose the smallest index among B, comma E, comma F and Z. The smallest is 13 for the vertex Z. Sorry, for the vertex F. For the vertex F here. So now select the smallest index in the above. In our case, the vertex F is the smallest index and let x equal to F. So we put here x equals to F here. Now, what will the path? Now, adding the F in the path P double dash. So we get A comma D comma C comma F, and remove F from, this is the P double dash, T double dash, and remove F from T double dash. We get B comma E comma Z. Now we have to reach at Z. That means we have to also calculate now for B, for E, and then lastly Z. Okay, so our here F is not equal to Z. We just chosen this F is not equal to Z, not a final vertex. So we continue and we repeat the same procedure here. So now select the smallest index in above. In our case, F is the smallest index and X equal to F. Now we create a new path here, P triple dash equals to A comma D comma C comma F, and new T double triple dash equals to, this will be B E Z. Now we have to find the smallest index among B, E, and Z. Now same calculation here, same computation here. Now T belongs to in T double dash. We compute the smallest index using the relation. The relation is this one. Here will be some modification. It will be in place of L double dash T, it will be L triple dash T equals to minimum of L double dash T plus L double dash D and plus W D comma T. Okay, now using this one, so we get, now first we take T equals to B. T equals to B here, because first element of T triple dash is B. So L triple dash B equals to minimum of L double dash B comma L double dash C. Just we chosen here X equal to F here, and the distance between B and F, B comma F. This is the relation here. Okay, so this is the relation here. L triple dash T equals to minimum of L double dash T comma L double dash X plus W of X comma T here. So using this relation, L double dash B, just we find this is 22, and L double dash F, that is 13, and B comma F, they are directly connected, and the weight is 7. So we put here 7. And this is the 22 comma 20, and equivalent to this is 20. So index of B in third iteration is 20. Similarly, we have to find for L double dash E, L triple dash E, we remove this one because F is not considering here, and L triple dash Z equals to, what will be? New value we see here. So similarly processing in this way, so this is 14, and L triple dash Z is 20. Okay. Now we have to find the smallest index among B, E, and Z. Okay. So the smallest index is 14 for the vertex E. For the vertex E here. So now select the smallest index in above. In our case, the smallest index having the vertex E. So we take X equal to E, in place of F we take E. Okay. Now we create a new path here. New path will be the fourth iteration of P. Then P triple dash union of adding the new path here, X equal to E here. So our new path will be A comma D comma C comma F and E, and remove E from the T triple dash. We get T4, fourth iteration of T equals to T triple dash minus E, and we get only B and Z, two vertex. Now we find the smallest index between B and Z. Okay, so our path is E is not equal to Z. It is not our final vertex, so we continue this process, and we create new path here. P4 gives the fourth iteration, which is A, D, comma C, comma E, F and E, and T4 is B, comma Z. Now for every T in T4, we compute the smallest index using the relation. Same, this is the same relation. Here we create T4 equals to minimum of L triple dash T comma L triple dash D. D here this is the element we have chosen here. Just we choose here x equal to, in previous slide we choose here x equals to, so E, so we put here E, so put E and W, E comma T, and T belongs to T4, that is B comma Z. Now find the smallest index for taking T equals to B here. So L4 B equals to minimum of L3B and comma L3E plus W B comma E here. So minimum of this one, L triple test B. We have to calculate this one here. In previous slide we calculate here. This is 20 and L double dash E is 14 plus weight of B comma E. B comma E, B and E is here, they are directly connected, so we put here 2, so this is 16, so minimum of this one is 20 comma 16, that is 16. Okay. Similarly for T equal to Z, so we get L4 of B equals to 16 and L4 Z equals to, similarly we find this is the 18. Now we have to choose the smallest index between B and Z, which is 16. Okay, the smallest index is 16 for vertex B. So now we choose the vertex B for the next procedure. So we take x equal to B here, and B is not equal to Z, not the final vertex. So we continue this procedure here. Now we create a new path here, P of V equals to. So we create new path here, P5 equals to P4 union of, just we select here B here. So this will be, the new path will be here A comma D comma C comma F comma E and B. A comma D comma C comma F comma E comma B, and what will be the T5? So T4 minus B here, so we get only our vertex Z here. This is the last vertex, this is the final vertex. So if you compute this one, so the value of this vertex is, what will the value of this one here? We take the relation. Now this will be L of for Z equals to, the formula will be minimum of L, sorry, this is the L5, Z equals to L of L4 of Z comma L for B plus W B comma Z. Because we choose here x equals to B here. Okay, the minimum of L double for Z is 18 here. L for B is 16 plus B comma Z. They are not adjacent to each other, so we put infinity here. Okay, we put infinity. Sorry, this is B or A, they are directly connected. Sorry, they are directly connected. So we put here 16 plus 2, then minimum of 18 comma 18. The minimum is 18. So what is the index of 18? The index of 18 is 18, and which gives the shortest distance from A to Z. The last value, the smallest index of Z, which is 18, and this will give the shortest distance. So here we stop the algorithm because Z equals to Z. We reach at our final vertex, so we stop the algorithm here, and hence the length of shortest path from A to Z is 18. From A to Z, the shortest distance is 18, and the shortest distance is achieved by the path. Just to see which path is achieved this value. So we see there the path is A to, this is A, B, C. This the path is A to C, C to E, and E to Z. A to C, C to Z. This is the length is 10 plus 4 plus 4, that is 18. So this is the your shortest path, A to C to E to Z. So AC EZ gives the shortest path, and we have to keep one thing in a mind, कि Dijkstra algorithm gives only shortest length from A to Z, and with the help of this we obtain the shortest path. Okay, so we find here कि the shortest distance between A to Z is 18, and which path achieve this value, we have to find that part. So here A to C to E to Z find is equals to 18 is the shortest distance. So our shortest distance is 18, and the shortest path is A to C to E to Z. Okay, so this is our shortest path algorithm, which is the Dijkstra algorithm, and which have the many applications in computer science here. So we conclude our lecture here. Now we will continue for next session. In this we study what is the tree and its applications. We will discuss in t equals to z and t equals to in next lecture we will discuss about the tree t and its what are the properties of tree, and what is the minimum spanning tree and minimum spanning tree, and then we use the Kruskal algorithm and Prism algorithm to find the minimum spanning tree. Thank you so much. Okay. Sir? Okay. Thank you so much.